P and Q belong to the set of real numbers such that 1 strictly smaller than P strictly and 1 strictly smaller than Q strictly smaller than infinity, and 1 by P plus 1 by Q is equal to 1. Okay. So P and Q are real numbers. They are strictly positive. Okay. They are strictly positive real numbers. Not only that, they are strictly greater than 1 also. And they satisfy the condition 1 by P plus 1 by Q is equal to 1. Okay. So what do we have? That let's look at this condition. So 1 by P plus 1 by Q is equal to 1. Observe the following fact. If P is equal to 1, we choose, what do we get? 1 divided by 1 plus 1 divided by Q is equal to 1, thereby implying 1 by Q is equal to 0, thereby implying Q must be infinity. Okay. Similarly, if Q is equal to 1, then 1 by P plus 1 by 1 is equal to 1, thereby implying is equal to 0, thereby implying P must be equal to infinity. Okay. So that case is not there. So P is equal to 1, Q is equal to infinity. P is equal to infinity, Q is equal to 1. So these cases are not covered here. Okay. If you look at these cases, this one. So we'll not consider this case. We can deal in this separately later. Okay. Now some property about this fraction. If you look at this one, what do we get? So 1 by Q is equal to 1 minus 1 upon P, which is the same thing as P minus 1 upon P. Upon P, that has to be 1 by Q. So cross multiplication, P is equal to Q times P minus 1. This is one thing. Not only that, this also implies what? This implies that P upon P minus 1, this is equal to Q. P upon P minus 1, this is also equal to Q. Okay. Now whatever has been done, if you replace all of these things, so let's look at this one. So 1 by P is equal to this one. 1 by P is equal to Q minus 1 upon Q. Okay. So what do we have here? Q is equal to P times Q minus 1. And so we have here P is equal to Q upon Q minus 1. Okay. So from here what we can say directly is that P is equal to Q upon Q minus 1, or Q is equal to P upon P minus 1. We can also say that P times Q minus 1 is equal to Q, and Q times P minus 1 is equal to P. Okay. And so 1 by P and 1 by Q could be written as in this manner. 1 by Q minus 1 upon Q. So this implies that 1 by P plus 1 by Q is equal to Q minus 1 by Q plus 1 by q, and clearly this is equal to 1 because q minus 1 plus 1 is just q, and q divided by q is 1. Okay, so this several relations we have, so we will be using this fact. Okay, indeed. So the moment we are having this thing, so p is strictly greater than 1, p is strictly smaller than infinity, or rather p is a real number strictly greater than 1, and similarly q. With this situation, let's talk about what is an Young's inequality, which helps in proving the Minkowski. Okay, and the Hölder inequality. Minkowski is the triangle inequality, so we will use to prove the Hölder inequality. Okay, so what do we have? Young's inequality. Suppose A and B, so this is proposition, belonging to the set of real numbers such that A and B are what? A and B are non-negative. Let P and Q belong to R and 1 less than P strictly less than infinity, 1 less than Q strictly less than infinity, and 1 by P plus 1 by Q is equal to 1. Then this says that the product AB is always less than equal to A raised to P, B raised to Q upon Q. This is the claim this identity inequality makes. The equality in Young's inequality occurs if and only if A raised to P to B raised to Q. Okay. So before proving the Young's inequality, we'll try to show this case that if it is equal, then this condition is satisfied. So let's assume for time being Young's inequality is true. Is true. That is, AB is less than equal to A raised to P upon P plus B raised to Q upon Q for all A and B greater than equal to 0, and 1 by P plus 1 by Q is equal to 1. P and Q strictly greater than 1, and they are real numbers. Okay. So assuming this inequality, let's say if the equality occurs, okay, that is only if part is A raised to P equal to B. So only if part, let's show. Only if and only if. So if AB A raised to P upon B plus B raised to Q upon Q, so this implies Q PQ times AB must be equal to what? Q times A raised to P. So P times B raised to Q. So this implies what? Shifting this on the right hand side, 0 is equal to Q times A raised to P minus PQ plus P times B raised to Q. Okay, so what do we have? But observe the following fact. So we'll use this equation. Observe the following fact is that 1 by p plus 1 by q is equal to 1. So this implies that 1 by p is equal to 1 minus 1 by q. So this is equal to q minus 1 times p, which is q minus 1 times p, is equal to q. So let's use this fact in here. So what do we get? So let's substitute this value here, this value of q. So 0 is equal to q minus 1 times p, a raised to p, minus, here it is ab, sorry, pq ab plus b raised to q. Okay, this is the case. So this is, now divide throughout by p. Since p is greater than 1, 0, q minus 1 a raised to p minus pq ab. We are dividing by p, so this becomes q ab plus p b raised to q. This is also dividing by p b raised to q. Okay. So let's look at the case. 0 is equal to, so let's separate these terms. So send e raised to q on the left hand side, sending this on the side, sending this term. So a raised to p minus b raised to q. Okay, this is equal to q times a raised to p minus qab, which is equal to q times a raised to p minus ab, or rather this is, again there is qa common, a raised to p minus 1 minus b, which is a raised to p minus b raised to q. Okay, again we'll use this kind of thing. Observe the following fact that a 1 by p plus 1 by q, this is equal to 1. So what do we get? 1 by q is equal to 1 minus 1 by p, which is equal to p minus 1 times q is p. So p minus 1 upon p, and shifting this q. So we have this one. So p minus 1, okay, and here is the case. So let's deal with this thing. Rather, what we would do is that you have this thing, so p. Let's substitute this value over here in this p, this value. So what do we get? P minus 1 times q. So a p minus 1 times q minus b raised to q is qa times p minus 1 minus b. Let x is equal to a raised to p minus 1. So this becomes x raised to q minus b raised to q. This is qa. Okay, this is qa times a raised to p minus 1 minus b. Another is because this kind of a thing is there, so we could factorize this. If P and Q so because this is true for all P and Q, P greater than 1 greater than 1, okay, and P and Q are what numbers? They are real numbers. So in fact this is true for all integers also, assuming, because this is true for all, assuming Young's inequality, we are assuming for all P and Q. So in this case, let's focus the case with Q belonging to the set of natural numbers. Okay, so if you allow that, then what do you get? So this gets factorized into x minus b, I'll drop this part, times x raised to q minus 1, q minus 2b, continue, the last term would be p raised to q minus 1, the left hand side, and the right hand side qa times a raised to p minus 1 minus b. What is x? X is a raised to p minus 1. So if you look at this object, this is x. So this is qa times x minus b. So what is common? So sending this on the left hand side, x minus b into, so x raised to q minus 1 and so on, b raised to q minus 1 minus qa. This is equal to 0. So we get that either x is equal to b or both of them. Zero or both of them are simultaneously 0. If both of them are 0, then this is the case, but the point is that this cannot occur. Why it cannot occur? If this is 0, so x was what? A raised to p minus 1. If this is 0, if this is 0, then the Young's inequality says that this is true for all a and p greater than or equal to 0. If this is the case, letting a, b, yes, you take it to be 1. So what you get, how many terms are there here? There are 3 terms, q terms here. So what do you get? 1 plus 1. So that is a polynomial of degree q minus 1. So with constant, this would be the constant of that x. So what would you get is that this is q times 1 minus q. This should be 0. Okay. In fact, that is satisfied. Yeah. But by letting x is equal to or 1 and choosing b to be equal to 2, so this becomes 1 plus so on. So say 1 plus 2 raised to q minus 1, and now this becomes as it is q. This is equal to 0. But what is the sum of these things? This is geometric sum. So that is 2 raised to q minus 1. So this implies that 2 raised to q minus 1 must be equal to q. And since q is any natural number, if you take q to be 2, So taking q is equal to 2, what do we get? 2 squares of 4. 4 minus 1 is 3. This is 3 and the right hand side is 2. So this is not satisfied. So this is a contradiction. In other words, this cannot be 0. So the only way this is true is x is equal to b. So if this is x is equal to b, what the case we have? We have that a raised to p minus 1 is equal to b. So raising on both sides the qth power. So a raised to p minus 1 into q is b raised to q. But since 1 by p is 1 by q is equal to 1, that forces that if you look at p minus 1, sending p on the right hand side. So p is equal to q times p minus 1. So this term is p. That forces a raised to p is equal to b raised to q. So we have come to the fact that if it is equality, then a raised to p is in fact b raised to q. Okay. So this is the case where assuming equality, we are getting this thing. Now let's prove the converse, the only if part. So converse. If a raised to p equal to b raised to q in AB so substituting here, AB is less than equal to a raised to p upon p plus a raised to p q. So AB is less than equal to a raised to p a raised to p times 1 by p plus 1 by q. But 1 by p plus 1 by q, this is 1. AB is less than equal to a raised to p. This implies b less than equal to a raised to p minus 1. But b, so if you look at this case, what is this condition itself is what? A raised to p is in fact, so if this is b raised to q, so okay, so that's right. So we have got this condition from inequality. So let's write that. B is less than equal to a raised to p minus 1, but b raised to q is a raised to p from given. So b is equal to, so this is from here and this is given part. This is from the Young's inequality. By substituting this value, but b is in fact what it is, a raised to p by q. But 1 by p plus 1 by q is equal to 1. So 1 plus p by q is equal to p. So p minus 1 is equal to p by q. So b is equal to a raised to p minus 1. This is from the given what we are concluding from here. So in other words, substitute here, a raised to p minus 1 is less than equal, is in fact equal to b and less than equal to a raised to p minus 1. Because there is a raised to p minus 1, this man p raised to p, in fact this is equality. In other words, the product This is equality. Okay. This inequality must be equality, and in that case, so you get that AB is equal to this thing, or there is alternative way also. So we have proved the equality. If you want A times B, which is equal to A into B is what? A raised to P minus 1. So that is A raised to P. AB is A raised to P. Okay. So if AB is A raised to P, again Young's inequality, AB is less than equal to A raised to P upon P plus B raised to Q upon Q. This implies that A raised to P, substituting value here, minus A raised to P upon P. This is less than equal to B raised to Q upon Q. So A raised to P to 1 minus 1 by P is less than equal to B raised to Q upon Q. But 1 minus 1 by P is 1 by Q. So A raised to P upon Q, B raised to Q upon Q. Q cancels. And here is also B raised to Q. In fact, it's equality. Either way you prove it. So what does this show? Is that the equality occurs if and only that is the case. That if A raised to P is B raised to Q. Okay. The graph of E raised to X, something like this. So here is 0, 1. Okay. This is X is equal to 0 line, or this is the origin at this point, or in other words, you just write it as 0, 0. So you have somewhere point here. Okay, E raised to 0 is equal to 1, which is this plot. No matter what it is there, if you take any X belonging to a real number, E raised to X is always strictly greater than 0. Okay, it's never negative, because E raised to minus example would be 1 upon E raised to 3 greater than 0. So this is the graph. Suppose let's take any 2 points on this thing, U and V. So what do I have? I have a point over here. This is U. This is a point V. Okay. So this is U comma. And this point is V comma. And the line joining these things. So line joining UV. What is the line joining UV? If you take T belonging to 0, 1, 1 minus T U plus TV. If you take the function, maybe say G of T, then what happens? G of 0 is in fact what? Is U. And similarly G of 1 is V. Okay. Now, so in other words, if you want to look at this one and you want to plot the 0, 1, it's a map from this interval to this interval, to the straight line. This interval, closed interval, to this closed interval. Okay. Similarly, looking at the quantity 1 minus T e raised to U plus T e raised to V. So here, if you look at this one, here is e raised to U, and here is e raised to V. Okay. So this segment this whole segment from here to here is the line joining this and this. Okay, the line joining this and this. And suppose if I call this as h of t, then what is h of 0? H of 0 is simply what? H of 0 is simply e raised to u, and h of 1 is what? E raised to v. Okay, this is the case. So the point is that in this kind of mapping, if you look at this thing, this maps 0, 1 to this part. Okay, so the mapping 1 minus ta plus tb, comma 1 minus t e raised to a plus t, not ab, where is a and b, u and v, sorry, which is what? 1 minus t u plus t a, comma 1 minus t e raised to u plus t e raised to v. This mapping, if you look at this 0, 1 to 0, 1, then what do we have? Just a little bit clear. Yeah, so you have this one at t equal to 0. The point is u comma e raised to u, okay, which is this point. At t equal to 1, it is v comma e raised to v, okay, which is this point. In other words, this kind of thing is a mapping from this to this thing. Okay. And because so what we are having, just erase this parts. This is the graph of e raised to. Yeah. So t 1 minus tu plus tv is somewhere a point between u and v. If you take this in, the u is strictly less than x, less than equal to. So it's a point lying in between, so somewhere is here. So if this is a point, maybe say x comma y, and this is your x, and its corresponding part y is what? Y is 1 minus t e raised to u plus t e raised to v is equal to y. This is this thing. Now observe that e raised to x derivative, the second derivative is e raised to x. So for all x belong to set of real numbers, so what do we have? We have that that we have shown that e raised to x is a convex function. It's a convex function. So what does this imply? This implies that if you take that point, so we have over e 1 minus tu plus tv. This is the point. This would be always less than equal to 1 minus t e raised to u plus t e raised to v for all u and v real numbers, such that u strictly smaller than v. Okay. If you take this kind of thing, then this is always true. Less than, you can take it equal also, but in that case it's just a singleton point. Okay. The convexity of this thing, this is the this is the value of the function. This is the value of the function. This is the secant of the line. Is lying always above. Okay. Now you take u to be the special case. So log of a raised to p, and similarly take v to be log of b raised to q. So, and take t to be 1 by q. That implies that 1 minus t has to be 1 by p, because 1 by p plus 1 by q, this is equal to 1. Okay. If you substitute these values, so substitute these values here, what do we get? Log of a raised to p. So you get that e raised to 1 minus t is what? 1 by p. 1 by p log a raised to p plus 1 by q log b raised to q. This value is less than equal to 1 minus t is 1 by p. 1 by p e raised to u. So this is e raised to log of a raised to p plus t is 1 by q, e raised to log of b raised to q. But so if you look at bracket this way, so what do we get? So this value over here, e raised to log is nothing but, so that becomes just a raised to p upon p plus b raised to q upon q. This becomes this is this value, and what is this one? So log, if you look at this one, so 1 by p here, it goes to the power, so that becomes what? Here is q. Okay, so what happens here? This is e raised to log of, this becomes to the power, is that clear? Log of this thing, a raised to p into 1 by p plus log of b raised to q into 1 by q, which is less than equal to a raised to p upon p as b raised to q upon q. So this is what? E raised to logarithm of a plus logarithm of b, which is nothing but logarithm of ab, is less than equal to a raised to p upon p plus b raised to q upon q. But a raised to log is ab, so this implies that ab is less than equal to this quantity. So I can just write over here, this is the Young's inequality, Hölder's inequality. Hölder's inequality. So what do we have? The Hölder's inequality says that if x belongs to LP, y belongs to LQ, PQ strictly greater than 1, PQ real numbers, okay, then what do we have? And x is in LP, so x is this infinite tuple, and y infinite tuple. Then the claim of this is that the summation mod xi yi, this summation is always less than equal to the pth norm of x and the qth norm of y. Okay. let's try to prove this fact. Assuming, so if x is 0 in LP, thereby implying x is a 0 tuple, thereby implying the product x1 y1 is the nth partial sum. This is 0 into y1, 0 into yn, and this is s. So this is 0, each of them. So the term is 0. So in other words, the summation, in this case xi yi, this is 0. And in that place, on the right hand side is norm x, cube norm of x times cube norm of y, and that is on the right hand side is also 0. Cube norm is 0, so it is verified. Similarly, if y is equal to 0, so we get the, it is also verified, norm of y is 0, the qth norm is 0, and so on, because the qth norm of y is what? Whatever this value is, 1 by q. This is 0. If this is 0, then each term is 0, then this is 0, and so on. And similarly, if you put there xi yi. So the point is that if any one of x or y is 0, it's trivially true. Hölder. So we assume x, y both non-zero, 0 tuple. In other words, the pth norm of x is non-zero and the qth norm of y is also non-zero. Okay. So let I belong to the set of natural numbers. Consider calling this A as mod of xi p, and calling B as q. So A is this, B is this thing. So clearly A is greater than or equal to 0. E is, so you take any, so it is fixing. So I could be 1, 2, 3 and so on. You can choose any one. So, but once you choose, you fix it, then you have A is greater than or equal to 0, B is greater than or equal to 0. So we can apply now Young's inequality. If you apply Young's inequality, AB is less than or equal to A raised to P upon P plus B raised to Q upon Q, where P and Q are what? Greater than 1 and belong to real numbers. Okay. Now if you have this thing, so let's try to substitute these values, A of this, B and this in this thing. This is less than or equal to 1 by P times mod of xi raised to P upon the pth norm of x, its pth power, plus mod of yi raised to Q y, its qth power. So the qth norm to the qth power. Here it is 1 by Q multiplied. Okay. If it is happening, let's write it properly. The pth multiplied by this norm is modulus, in this case they are real number. Qth power. Okay. So this is for one particular I. It is fixed. So let Sn is equal to rather we just multiply here itself, divide by one to n. This is the partial sum of the series. This thing, let Sn dash I going from 1 to n mod of xi pth power, its pth power. Okay. And Sn double dash, let it be as 1 to n mod of. Okay. So Sn double dash is the qth norm, and we have that Sn less than equal to 1 by p Sn dash q Sn double dash. Observe that. Okay. Observe that norm of x infinity. This implies that 1 is equal to the pth norm. In other words, the S dash is equal to 1. That is the limit of Sn dash. Similarly, S double dash is also 1. You will have q here and yi is in double dash. So as n tends to infinity, you are taking limits on both sides. We're taking S is less than equal to 1 by p S dash plus 1 by q S double dash, but this is 1, this is 1, so S is less than equal to p plus 1 by q, which is equal to what? It's already 1. So S is less than equal to 1. What was S? S was nothing but summation xi, yi, norm x, p, norm y, q, I going from 1 to infinity. And so this is less than equal to 1, sending, this is a constant term of each, the limiting, so each partial sum won't have this thing. So what do we have is that this goes on the right hand side, and we have the required fact is that this implies the Hölder equality. That is okay. And X is that finishes the part of the proof. Let LP so from here, shifting on the right hand side, we get that P is equal to Q is equal to, and so on. What do we have is that raised to P, I going from 1 to infinity. Okay, there, this is the case. The moment you have this thing, it can be used this fact, this one. To the norm of X, P. Whole raised to Q. You have this thing. P minus 1 over here. Okay. In other words, if X is X1, X2, and so on, W is the object, which is mod X1, mod X2. So this is P minus 1. This is the case. Then W belongs to LQ because this becomes what? Select this is W1, W2, and so on, so on, so on. Norm of X, P raised to P is it's a finite number. It's a finite number. So this is norm of W, the qth norm of W raised to the qth power. So we have this thing. Okay. So we'll use this fact. Okay. To prove Minkowski inequality, which is precisely nothing but the triangle inequality for LP spaces. Let's consider. So let's write the statement. Minkowski inequality. Let LP one by P is equal to 1. Similarly, Q also greater than 1. Okay, this is the case. And the claim is that norm of x plus y, the pth norm of this thing is less than norm of this thing, pth norm, and the pth norm of y. Okay. Proof. Let's look at the term in this thing. Mod xi plus mod yi raised to p. So norm of x plus y, the pth power is equal to, this is the limit of this series. So if you take the partial sums of the series, they converge to a number. That number is this one. Okay. So let's wrap this up. So norm of x plus y is p 1 to infinity of mod of raised to p. Now this could be, this is the same thing as what? Summation mod xi. So of course we are dealing with the partial sums. Just as a notation, is this thing. This could be written as what? This times as a real number p minus 1. Okay. Now this is less than equal to this triangle inequality for this one. So because for real number yi, so what do we have? If we write partial sums and so on, this is less than equal to from 1 to infinity mod xi plus yi, so p minus 1 plus summation I going from 1 to infinity mod yi mod of xi plus yi. It's what power? It's p minus 1 power. Okay. And you have this thing. See, if this was the term of x plus y, so if you observe, let me write here, x plus y would be x1 plus y1 and so on, so on, so on. This term would be x2, rather let's write second term x2 plus y2, so on, so on, so on. So the w term also here, considering mod of x1 plus y1, it's a p minus 1th power. Mod of x2 plus y2, it's p minus 1th power. Then we have seen that this W dash belongs to LQ. Okay, this belongs to W dash, it belongs to LQ. So what can be said is that the term, so if you look at here, let me write X belongs to LP, W dash belongs to LQ. Similarly, Y also belongs to LP. We apply Hölder's inequality. So we get that this is the pth norm, which was less than equal to norm of X pth time norm of W dash plus norm of Y pth norm times the norm of W dash, its qth norm. Okay. So what is common from here? Norm of X plus Y, pth norm of P is less than equal to into bracket norm XP norm Y. This is the thing. But what is W dash? Yeah, so the W dash is nothing but mod of, let's write that. So W dash P minus 1 power and so on. So this is this term, it's qth norm and so on. So this is nothing but so this term is there, W dash is there, and so on. And the claim is that W dash is to P minus 1. Not raised to P minus 1. W dash is in fact what? As we have seen earlier, norm of W dash, the qth norm of Q is equal to norm of X plus Y of pth norm, the pth power. So this implies that norm of W dash is equal to norm of X plus Y. Taking P by Qth power, these are real numbers. P by Q. So what do we have? What we had. Okay. Now we have this fact that W dash normal, the qth norm of this is the same thing as norm of P. If you look at this thing, let's do a simplification. Since 1 by P plus 1 by Q is equal to 1, this implies that multiplying by P So P by Q is equal to P minus 1. So this term over here, this becomes P minus 1. The norm of the qth norm, the P minus 1th power. Okay. This becomes the 1th power. Let's substitute this value, which is this one over here. So if you substitute that, norm of x pth power x plus y, its pth norm raised to what power? P minus 1 norm x p norm y p. Okay, now this is P minus 1 power, this is dividing by this thing, they are non-zero. So what we get is and this is the triangle inequality what we want for LP spaces, which is the Minkowski.